Is it visible now? Like now, is it visible?
Yes, it is
I mean,
visible.
the writings are visible now.
Yeah, the theorem one. Yeah, it is visible.
Yeah. Okay. So the main result of this paper is like there exists a Monte Carlo algorithm for checking if a graph is Hamiltonian or not with n vertices, and it has a running time of O star 1.647 to the power of n, and has an error exponentially small in n. Now, since this is a randomized algorithm, there has to be an error, and we need to diminish that error as much as we can. And this result can be improved for like special kind of graphs like graphs with independent sets or in specifically bipartite graphs as well. So for those kind of graphs, if the conditions are same except that it has an independent set of size I, then we'll have the Monte Carlo algorithm which runs in O star to the power of n minus I. Again, the error is exponentially small in n. Now, this brings us to another important problem, which is the traveling salesman problem. This is very closely associated with the Hamiltonicity problem. So, what is this traveling salesman problem? It says that if you are given a complete graph which is weighted, in other words, the edges are weighted, like we can see here the 10, 25, 25, 15, 30, 30. These are all the weights of the edges. And we are interested in finding the Hamiltonian, I mean, not the, yeah, you are interested in finding the Hamiltonian cycle which has the lightest weight. Like in this case, the cycle marked in red is the lightest Hamiltonian cycle. And we need algorithms to find this. And for this, we again have another Monte Carlo algorithm to find the lightest TSP2 with positive integer edge weighted graph on n vertices, which runs on O star W times 1.65 to the power of n, where W is the sum of all the weights of all the edges. Again, the error is exponentially small in n. A better deterministic, I mean, not better, I would say that a deterministic algorithm also existed. It's also a very famous one, known as the Bellman-Heldkopf algorithm, which uses dynamic programming to find if a complete graph, to find a light TSP2 for a complete graph. So how does it do? Like in dynamic programming, we store stuffs and then use those information to proceed further. Like if we have n plus two vertices of a graph, if we have a graph with n plus two vertices, and we will store the lightest path between any two vertices of the graph, which covers all the other edges, all the other vertices as well. We will consider any two vertex and we'll take the path which covers all the other vertices and is the lightest one. Using this information, we can proceed further. How? If we add another vertex to that graph, which is n plus two vertices, and we want to find the lightest path between the starting and the end point, we will find, let's say this is the graph, and by this arrow I mean the 2. So this starting point is the starting point, this vertex is the starting point, and we have the information regarding what is the shortest path between this starting vertex to all the other vertices. We have this particular information. And suppose we add another new vertex and we want to find the lightest path between the starting and the end vertex. So what can we do? We will pick up that vertex which has the lightest path between the starting and the end point, starting and this point, covering all the other vertices. This is the lightest one among all the vertices. And then we will add this weight. So this, if we represent it numerically with an equation, this is somewhat the equation looks like, where WST represents S represents the starting point, T represents the end point, and X represents all the vertices that the path needs to cover, including S and T. So what is it? It is the minimum of the weighted paths from S to U. U is the vertex. U is a certain vertex which we are taking from X apart from S and T. We're taking the minimum of that and then we are adding the weight between this vertex and the end vertex. So this gives us the lightest path between the start and the new vertex. The running time of the algorithm is O of n squared times to the power of n. There is a very good Wikipedia article on that. If you're interested, you can have a look on that regarding how to calculate the running time. Like it's pretty trivial to understand like how the stuffs are going on. The organization of the paper. So we will first describe what a labeled cycle cover sum is, and and how is it related to Hamiltonicity? Like how can we use this label cover sum to relate to Hamiltonicity? And then we will finally focus on the reduction of Hamiltonicity to the labeled cycle cover sum. Now the labeled cycle cover sum has the main idea of counting weighted cycle covers. So what is a cycle cover after all? Like what is cycle cover? So let's try to understand what a cycle cover of a graph is. So suppose we have a graph such that every vertex in the graph, for every vertex in the graph, there exists exactly one arc which starts at that vertex, and there exists exactly one arc which ends at that vertex. So the collection of these arcs form a cycle cover, which looks something like this. If we have a close look on this, we see that these are all disjoint cycles which are covering all the vertices. So this is why we have the name cycle cover of a graph, because we just have disjoint cycles which cover all the vertices of the graph. Now we will define what a labeled cycle cover sum for directed graph is. Now for a directed graph D, we will consider a label set L. Label set, by label set we mean that we will be labeling the arcs with certain elements. Like we will consider this label set L, and CCD is the family of cycle covers. Then we'll consider the labeled cycle cover as labeled cycle cover sum for directed graph as this particular thing. So what is this sum all about? Let's try to understand. Like we are taking a C, which is the cycle cover from the family of cycle covers. Then we are considering a function which labels this cycle covers with, I mean, we are labeling the arcs of this C, and then we're considering each arc of that C and then plugging them in this particular F. Now this F has this particular F is a particular function which has a domain which is a ring, and it takes elements from, as we can see that it takes elements from C, the arcs, and then G inverse of A represents all the elements of L, so it's 2 to the power of L. Right? So this is what the labeled cycle cover sum for directed graph is. Now I would like to say that the codomain of this function F is really important, as we'll be using that to find Hamiltonian graphs. So here F is, as I described, that F is just a function from A cross to the power of L, excluding the phi to R. R is just a ring. And another notation, HCD is the collection of cycle covers which contain a cycle covering all the vertices. In other words, it's just a subset of CCD which has a Hamiltonian cycle. Now, since Hamiltonian cycle itself covers all the vertices, so it is like a Hamiltonian cover is just the Hamiltonian cycle itself. And HCD, in other words, is just a collection of Hamiltonian cycles. Now, using this sum, we need to cancel out the non-Hamiltonian cycle covers because we are mainly interested in finding the Hamiltonian cycle covers. So how can we do that? We'll consider the ring R, which is the domain of the function f, to be of characteristic 2. So how can we use this fact? We'll define a special type of function f, which is also called the S-oriented mirrored function, such that if we take uv, then f of uv comma z, z is just a subset of the label set, f of uv comma z equals f of vu comma z for all z, and u and v must not be equal to s. So apart from u and v being equal to s, f of u v a comma z equal to f of vu comma z, we have to equate these things. And for a directed graph B and for a level set L, and if we consider f to be S-oriented mirror function as we have described in the earlier slide, and we are considering here a domain ring of characteristic 2. This is the following sum that we will get. You can note that, like unlike the previous description of this sum, this is not CCD, instead this is HCD. So this is the thing that we get after describing this f to be S-oriented mirror function and the domain ring we're considering to be of characteristic 2. So what is the idea? The idea is that every non-Hamiltonian path can be contributes equally to that sum, because we have described the function to be S-oriented mirror function, which is just f of u v comma z equals to f of u comma z. We're just flipping the orientations. We can see, like in this example, these two are non-Hamiltonian covers, and this is the orientation of B, and this is the orientation of A. So we are considering the first cycle of the non-Hamiltonian cycle covers, which does not cross S, and we are flipping them. So these two contribute equally to the sum. And since the ring is of characteristic 2, they add up and nullify each other, leaving only the Hamiltonian cycle covers. Now, Hamiltonian cycle covers need not, I mean, we should be careful regarding, like, the Hamiltonian cycles should not kind of cancel each other. And even with the opposite orientation, they must contribute different terms to the sum, unlike the other cycle covers, non-Hamiltonian cycle covers. And in future, we will define f in such a way that the level cover sum seen as a polynomial, we will be saying that this level cover sum can be visualized as a polynomial. And this polynomial will have at least one unique monomial per Hamiltonian cycle. So this is the kind of representation that we'll be using in future. Now, if there isn't any Hamiltonian cycle at all, then the polynomial must be 0. So how to check if a polynomial is identically equal to 0? So for that, we have a few theorems and lemmas. The first one is the Schwarzschild lemma. The Schwarzschild lemma says that if we have an n-varied polynomial and we take a subset f from the domain, from the codomain, if we take a subset f and uniformly randomly we pick up certain variables and plug it in the polynomial, the probability that this polynomial will give us 0 is less than or equal to the degree of the polynomial divided by the cardinality of f. F is the subset that we are taking the values from. Now this Ri, R1, R2, Rn, these are all chosen uniformly randomly. And determinants and inclusion exclusion. So we have an idea regarding what the definition of determinant is. It's just a summation and a multiplication of stuffs, and we're adding, subtracting stuffs from there. So in a field of characteristic 2, the determinant and the permanent have the same definition. So what is a permanent? Permanent is same as a determinant, but we are excluding the minus signs. Instead, we are adding all the stuffs. Like while calculating determinants of matrices, we minus certain stuffs. In case of permanent, we don't minus anything, we just add all the stuffs. So since in characteristic 2, they both mean the same thing, these two definitions coincide. So the determinant is actually equal to the permanent, which is the following definition. And yeah, of course, this A is the adjacency matrix, and sigma is just a permutation of it. Now, permanent can be associated with the weight level covers. So how is it done? So if we consider A as the weighted adjacency matrix, like instead of writing 1, we are just writing the weight of the edge ij. We can define the permanent of that matrix as in the following way. This is actually a remarkable result in which we are associating sums of determinant or the permanents with weight level covers. And this is actually an important result as we'll be using this idea pretty often. Now, this level cycle cover sum can be evaluated through the sum of determinants. Now, this is actually a very important idea of this paper, as the title suggests. The determinant sums play a very important role in finding whether a graph is Hamiltonian or not. So if we so here we will be considering a matrix MFZ I comma j, where the I comma jth entry will be f of ij comma z, where ij is just an entry of a. I mean, by a we mean the set of edges. So ij is just an edge, and z is considered to be non-empty, and z is again the subset of L. And for all other entries, we'll consider this to be 0. Further, we'll define another entity, that is P of F comma R, which is the summation over all the subsets of L, and finding the determinant and determinant of the summation over all the subsets of Y. Then R times to the power of Z, the cardinality of Z, times MFZ. MFZ is just as we have described. This might look a bit complicated, but I know it's a bit complicated to memorize this, but we can. But this is actually pretty important in future results. And this is a remarkable result. Like, we are associating the sum of determinants and the level cycle cover sum. So again, I'm not going into the proof of this. I'll be sharing the paper. If you are interested, then you can have a look. But this is actually a remarkable result where we are associating the sum of determinants exponential number of determinants with level cycle covers. Now we have to the number of operations. Now, one of the most important thing is like how much time will the operation take. Like, we have to calculate the sum after all. So how much time will it take? Well, the time it takes is represented by this. This thing is a bit complicated again, but again is very important. Here, omega is a certain constant which we get on multiplying two square matrices. Like, it depends on the algorithm we use to find the product of two matrices. Like in this case, omega is 2.376. This is just to evaluate the sum lambda. Now we will focus on how we can reduce this idea to Hamiltonicity. I mean, how we can reduce Hamiltonicity to this idea, like the sum of level coefficients. So let's begin with bipartite graphs. And let's take the bipartite graphs G, V1, V2, E. And V1 and V2 are just the bipartition. And we'll fix S in V1. Now, this S is a special vertex in V1, and on the basis of this, a lot of things will depend. And for every edge U comma V, and for every edge UV in E, we will define variables, that is XUV and XVU. We will equate them if V or S is not equal, like V equal to S or U equal to S must not be true. XUV equal to XVU except for V equal to S or U equal to S. Except for this, they must be equal. And for U comma V in V1, we will describe the neighborhood of U comma V as all the vertices on V2 such that UW is an edge and WV is an edge. In other words, like there is an edge between U and W, and there is an edge between W and V, and W is in V2. Now we define another graph. Like, this is a different from the graph we take in input. This graph considers V1 as the vertices and F as the set of edges. Now, what is F? F includes the arcs in both the direction for every U and V in V1. Like, for example, this. Like, we're taking this edges. Like U, suppose this is V1, and this is u and v, then we're taking both the edges in both the directions. This is the graph we're defining as D. And we also must make sure that the neighborhood of u comma v must be non-empty. Then we define the function f, which will take uv as an input, which is an arc, and for w, like if w is just one of the members of the neighbors of u comma v, and we'll define this in the following way. It is xuw and xw. And in all the other cases, f will return 0. So the first thing, this is an important lemma that the sum can be represented in this particular way. So this is a polynomial representation. This is like this is one of the most important thing that we'll be using in this reduction. Like that lambda d v2 of v2 comma f will be equal to this particular sum. So we can note that d is the graph and v2 we are considering as the label set. So we are labeling all the vertices of v1 with v2, like not the vertices, the arcs. And the second thing is that this polynomial is a zero polynomial if and only if the set HCG is phi. In other words, there are no Hamiltonian cycles. There are no Hamiltonian cycles, this polynomial will be zero. So these are two important points. So what is the algorithm for reducing the idea of Hamiltonicity in bipartite graphs to this sum? So we will repeat a certain process linear number of times, linear in n number of times. The idea is to reduce the error we get. Now again we will consider G to be a bipartite graph, which is with the bipartition V1, V2. And of course we have to note that the cardinality of both V1 and V2 is n over 2, where n is the number of vertices in it. Now we have seen that how we can associate this bipartite graph to this sum. In the previous slide, we have seen that how we can associate this input of bipartite graph to a label of a label cycle topology. So we will be using this idea, and then we'll be choosing a k which is large enough such that e to the power of k is greater than c times n, where c is some real greater than 1. And now we'll be using the idea of Schwarz-Zippel lemma, where we have to check if a polynomial is 0 or not. So how did we do that? We just took a set and plugged in random values from there into the function f, or in this case the polynomial, and we checked that if that is equal to 0. So by Schwarz-Zippel lemma, the probability that the polynomial is identically non-zero if a certain run is non-zero is 1 minus 1 over c. We can check this out. Like we can use the Schwarz-Zippel lemma and directly follows from there. That if a polynomial is identically non-zero, if a certain run is non-zero, then the probability of that happening is 1 minus 1 over c. And if the result is non-zero for any run, we will output that the graph is Hamiltonian. Now, of course, this has an error as we have seen. So for this reason, we will repeat the process multiple times so that we can reduce the error. And we can finally reduce this to e to the power of minus omega big omega of n. And the probability of the false negative will become e to the power of minus omega of n. And to do this, the runtime, as we had mentioned earlier, that huge big entity that we had seen for calculating the lambda, the runtime, as we have seen in this case, if we plug in all the values, you get to see that this is nothing but O star of to the power of n by 2. And if we have a closed node, then we'll note that this L is actually V2. That is the second bipartition, as we are labeling all the graphs of D using the vertices of V2. Now, this was the case for bipartite graphs. So, what is the case for the general? What is the condition for the general case? Like, is it different? Like, of course, it is different because we don't have a bipartition, and that is a bit problematic. We have to be a bit careful with that. What can we do? Suppose we have two partitions of the vertices. Like, let's consider this. So we will partition the vertices of the graph into V1 and V2, and then we will label them in a very specific way. How can we label them? We will label if we have the V1 over here and any two vertex which is a part of the Hamiltonian cycle, like you can see that this is a Hamiltonian cycle. Any two vertices in V1, any two consecutive vertices in V1, if they are a part of the Hamiltonian cycle, we will consider them as unlabeled by V2. We'll consider them as unlabeled by V2. And all other arcs will consider to be labeled. So as we can see that this green thing is unlabeled. So what are we doing in this? So we are partitioning a Hamiltonian cycle into a set of labeled and unlabeled arcs by V2. In V2 we are using V2 for labeling stuffs, and we are keeping certain edges, certain arcs which are unlabeled, which must be kept unlabeled. And this is the partition of the Hamiltonian cycle into the labeled and the unlabeled arcs. We'll look at a certain definition which says that HCV2M of G is a subset of HCV. So what is this HCV2M? This HCV2M is a subset of the Hamiltonian cycles H which contains precisely M unlabeled arcs along H. So this is the thing that we're introducing further after HCG, because this is not the case of bipartite graphs. Now for every edge UV in E, we will define two variables, just like the previous cases. We will define two variables, XUV and XVU, such that U is in V2 or V is in V2 or both are in V2. And they equate. That means that XUV will be equal to XVU, except if V equal to S or U equal to S. It is the same as the case for bipartite graphs. So this is the thing that we are defining, these variables we're defining in this particular way. And additionally, we'll be introducing another label set, which deals with the unlabeled arcs. Like we have seen that there are certain unlabeled arcs which are not labeled by V2. So to deal with them, we will define another label set, that is LM, which contains M extra labels to deal with the unlabeled arcs. And for every U, V in GV1 and every D in LM, we will define these two variables, which again follows this condition, that is X of V, D will be equal to X VU, D. And further, we will define this function f of u, v, x in this particular way. Now, what is this stylish p, u, v, x? So this means this is the set of simple paths from u to v. That will be equal to, we'll consider that to be equal to x u v comma d. Now again, what we are doing here is trying to is a zero polynomial if and only if HCV to MG is phi. And this is the main idea where that will be using in the algorithm. That this particular polynomial is zero if and only if h0 to mg is pi. So what's the algorithm? Well, we will randomly partition the set of vertices into v1 and v2, and then we will now this algorithm will loop over all the number of unlabeled arcs by v2 from 0 to n max. Now what is n max? N max is the maximum possible for unlabeled arcs that we can get. So the algorithm will run over all these n's from 0 to n max, and we will choose k as earlier, that is we have to choose k large enough such that 2 to the power of k is greater than cn. This is the case for bipartite graphs, and this is the thing that we have seen, like for a certain given graph we can associate this sum to the input, like just like in the case of bipartite graphs, we can associate the input to this level capacity. Now we will choose values uniformly at random from the field. I'm sorry for the typo, but so we will take random values from the field and we will plug them into the cell. So just to mimic whatever is going on in Schwarzschild. Now for calculating f on random set of variables for all subset of V2, we will use a recursion which is similar to the Bellman-Hartnett algorithm, which is to use the concept of dynamic programming, like we are storing certain stuffs and we'll be using those stuffs to proceed further. Like for this case, we'll define f cap as a function which is defined in the following way. And we see that f of fuv comma x is actually equal to f cap uv comma x, where we're taking x as a subset of v2. And to proceed further, we will see that f of uv comma x can be described as a following sum. So why is that so? We note that we are excluding this w, like we are including the w later. We have this particular sum, and as we're including this w later, we will have to multiply this, like we have to multiply this particular entity, as we are missing this out over here. We'll be missing this out, so we'll have to multiply this identity externally, and then we have to apply f cap on this thing. So this is just a recursive relation that follows, and using this recursive relation we can calculate what f actually is. Now finally, we will evaluate the polynomial for randomly chosen values in each run, and if it returns non-zero value for any run, then we will conclude that the graph is Hamiltonian. Again, it has a running time, and so what is the running time? Let's have a look. So the tabulation for f, like for all the subsets of V2, we were tabulating certain values using the recursive relation. So that will take the time O star to the power of n by 2. And for the worst case scenario is when n is actually equal to m max. And for that condition, we'll have this increment in time O star of to the power of n by 2 plus n max. And the total number of runs we're considering to be r. So the total becomes O star r times to the power of 0.5 times n plus n max, and the probability of false negatives becomes this, because the summation is, as we can see, that ACVM to the sum of all the stuffs is equal to 0 must be the case of false negatives. And as we are running this over r times, so we have the power r over here. Now, to reduce this error to exponentially small, we have to reduce this to exponentially small error. We'll be using another lemma, which is again a huge entity, that is this thing. And this requires a bit of calculation to proof and other stuffs. And we can use this idea to reduce the error of false negatives to e to the power of minus omega n. And as we try to reduce this error, we will get that m max must be equal to 0.205, and the number of runs that are required is n to the power of O of 1 times 2 to the power of 0.024 n runs. And if we plug in all together, we will say that this is the upper bound for finding if uh, this is the running time. This is the upper bound for the running time of the algorithm for searching if there exists a Hamiltonian path, a Hamiltonian cycle at all. Thank you, everyone. I hope I am able to convey something fruitful to this session. And yeah, that's it. That's all I have to say for this talk.
Thanks, Ishan. Anyone has a question? I guess they are effectively
Hi, can you share some reading material on it?
Yeah, I'll be sharing the paper. The entire paper I'll be sharing. Okay, let me share it right now. Like if I have missed certain details, then yeah, if you want, you can check that out. It's a very good paper.
okay. Anyone else?
Yeah, I'll share the paper.
Yeah. Okay. I guess that's it then.
By the way, one thing I will mention that in the meantime I lost connection for a while, about 2 minutes. So that time I wasn't able to record.
Yeah, like you have recorded it into two disconnected parts, right? We can like always join it and make a single video. Like some parts will be missing. Yeah.
Yeah.
Yeah, like I guess from tomorrow I can share you some my Microsoft meeting link, and you can always sign in through Gmail accounts to Microsoft meetings. And in Microsoft meeting, the recording part is very easy. So